Now that we know what a Jacobian is and two different ways we can calculate that in Python, let's take a look at another concept known as Frenet-Serret formulas. What the Frenet-Serret formula will help us do is calculate these three vectors, that two of which we will use in order to find the plane in which our circular cross sections for the hose will exist. So let's take a look at our curve one more time. So we have this curve, and what we need is a tangent vector, a normal vector, and a binormal vector that's normal to both of the tangent and the normal vectors. And we need to find these at any point on the path of the helix or the spiral. Now, what we have according to the Frenet-Serret formula is the normal vector, or the unit normal vector, is equal to the derivative of the unit tangent vector with respect to the arc length. Now, we already know what the tangent vector is. It is simply the Jacobian of our function, or let's write this as df over dt. Now, what we can see from here is that if we use chain rule in this formula, this turns into the derivative of the tangent vector with respect to time times dt over ds. Now this term right here is simply another Jacobian, so that would just be the Jacobian of our function. That will give us the tangent, or it wouldn't give us tangent, it would give us the derivative of tangent with respect to time. Now, we can write this as Jacobian of our Jacobian divided by ds over dt. Now, let's take a closer look at one of the sections of our spiral. So we have this arc, and it's got a center right here, and now I'm going to extend two radius from these places. Say this is the radius at time t, rt, and this would be the radius at time t plus dt. So rt plus dt. Now, if dt is small enough, the small increment in time is small enough, the arc length can simply be approximated by this length right here, which basically is our derivative of our function dt. So arc length can be approximated by df over dt if dt is small enough. Another thing to notice though is that this thing right here is a scalar quantity. It's an arc length. So this would simply be the magnitude of df over dt. So this would simply be written as this. And since this is also a unit vector, at the very end we would have to actually find the magnitude of n and divide it by the vector. So n vector divided by the magnitude would finally give us the unit vector. So let's go ahead and try and do that on Python. So let's write a function that would give us both the tangent and the normal vectors at the same time. So let's define the function as Frenet-Seret, and this will take our any function as an input, and it will return to us the tangent as well as the normal vectors. So first of all, in order to calculate our tangent, we know that we need the Jacobian of our main function. So let's call that df dt, and that would simply be equal to Jacobian of our function f. There we go. Now we need to find out how to calculate ds over dt. So let's do that by using a function. Ds dt, let's call that a function, and this function would take time as an input, and then what we can do here is basically we want this to return the magnitude of df dt. So there's an easier way to do this in Python using JAX NumPy. So basically what we need to type is jnp.get linear algebra dot norm for normalize, and we will simply feed this df/dt that takes time as an input. So that will give us our ds/dt. And then our normal vector would simply be, I would write this as def tangent, and this will take time as an input as well, and this will return to us df/dt, which takes time as an input, and divides that by ds/dt, which also takes time as an input. So that will give us our tangent in a normalized form, because we're dividing it by the magnitude, so we can get the unit vector. After this, what we need is the normal. So for the normal, we also need the Jacobian of the tangent. So let's call that d tangent over dt. And this will simply be a Jacobian, so that's again Jax dot Jacobian f, and takes the function f. So that's the Jacobian of our, so that would be the Jacobian of our tangent. Now in order to get the normal, what we can do is define another function, def, let's call it normal, and takes time as input, and we will want this to return d tangent underscore d tangent underscore what is this, dt, takes time as an input, and divide that by ds/dt, which also takes time as an input. So there we have all of our functions. Now another interesting thing about this calculation is that we can now find the curvature of our curve, which is actually simply the reciprocal of our normal vector of it. So simply put, it's just 1 over Jax dot JNP dot linear algebra dot norm, and we would feed this our curve. Let's do it at the coordinate where time equals 0. Okay. Let's see. Is this Jax? That's strange, that's not true either. Okay, I see. I think we have to run the whole thing one more time. So there's that. Hopefully that works. All right, there we go. So the curvature at t equals 0 would simply be this value. Yeah, so like one last thing we need to do in order to get our normal vector is actually divided by our unit vectors as well. Divided by the magnitude, so we can actually get the unit vector. So what we need to do here is, I will say v equals this value, and we would simply want this to return v divided by jnp dot linear algebra dot normalize v. So that would give us the coordinates of the vectors for our tangent as well as our normal.